For any help regarding advanced network design assignment, help. Visit https://computernetworkassignmenthelp.com/https://computernetworkassignmenthelp.com. Email support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or call us at +1 678 648 4277. Problem 1. Extreme FIFO queues. Design a data structure that maintains a FIFO queue of integers, supporting operations enqueue, do, and find min, each in O(1) amortized time. In other words, any sequence of m operations should take time O(m). You may assume that, in any execution, all the items that get enqueued are distinct. A. Describe your data structure. Include clear invariants describing its key properties. Hint: use an actual queue plus auxiliary data structures for bookkeeping. Solution: for example, we might use a FIFO queue main and an auxiliary linked list, min, satisfying the following invariants. 1. Item X appears in min if and only if X is the minimum element of some tail segment of main. 2. Min is sorted in increasing order, front to back. B. Describe carefully, in words or pseudocode, your enqueue, dequeue, and find min procedures. Solution: enqueue X, 1 add X to the end of main. ComputerNetworkAssignmentHelp.com. 1. Starting at the end of the list, examine elements of min and remove those that are larger than X. Stop E, add X to the end of min. Enqueue X, 1 add X to the end of main. 2. Starting at the end of the list, examine elements of min and remove those that are larger than X. Stop E3, add X to the end of min. Dequeue 1, remove and return the first element X of main. 2. If X is the first element in min, remove it. Find min 1, return the first element of min. C. Prove that your operations give the right answers. Hint: you may want to prove that their correctness follows from your data structure invariants. In that case, you should also sketch arguments for why the invariants hold. Solution: this solution is for the choices of data structure and procedures given above. Your own may be different. The only two operations that return answers are dequeue and find min. Dequeue returns the first element of main, which is correct because main maintains the actual queue. Find min returns the first element of min. This is the smallest element of min because min is sorted in increasing order, by invariant 2 above. ComputerNetworkAssignmentHelp.com. The smallest element of main is the minimum of the tail segment consisting of all of main, which is the smallest of all the tailments of main. This is the smallest element in min, by invariant 1. Therefore, find min returns the smallest element of main, as needed. Proofs for the invariants. The invariants are vacuously true in the initial state. We argue that enqueue and dequeue preserve them. Find min does not affect them. It is easy to see that both operations preserve invariant 2, since a dequeue operation can only remove an element from min, the order of the remaining elements is preserved. For enqueue X, we remove elements from the end of min until we find one that less than X, and then add X to the end of min. Because min was in sorted order prior to the enqueue X, when we stop removing elements, we know that all the remaining elements in min are less than X. Since we do not change the order of any elements previously in min, all the elements are still in sorted order. So it remains to prove invariant 1. There are two directions. The new min list contains all the tailments. Enqueue XX is the minimum element of the singleton tail segment of main, and it is added to min additionally. Since every tail segment now contains the value X, all elements with value greater than X can no longer be tailments. So, after their removal, min still contains all the tailments. Dequeue of element X. The only element that could be removed from min is X. It is okay to remove x, because it can no longer be a tailman since it is no longer in main. All other tailments are remain in min. All elements of the new min are tailments. In Q, xx is the only value that is added to min. It is the min of the singleton tail segment. Every other element y remaining in the min list was a tailmin before the enqueue and is less than x. So y is still a tailmin after the enqueue. Computer Network Assignment Help.com. Deque of element x. Then we claim that, if x is in min before the operation, it is the first element of min and therefore is removed from min as well. Now, if x is in min, it must be the minimum element of some tail of main. This tail must include the entire Q, since x is the first element of main. So x must be the smallest element in min, which means it is the first element of min. Every other element y in min was a tailmin before the deque, and is still a tailmin after the deque. D. Analyze the time complexity, the worst case cost for each operation, and the amortized cost of any sequence of m operations. Solution: deque and find min are O1 operations in the worst case. In Q is O, m in the worst case. To see that the cost can be this large, suppose that enqueue operations are performed for the elements 2, 3, 4, m-1 m in order. After these, min contains 2, 3, 4, m-1 m. Then perform enqueue 1. This takes omega m time because all the other entries from min are removed one by one. However, the amortized cost of any sequence of m operations is O, m. To see this, we use a potential argument. First, define the actual costs of the operations as follows. The cost of any find min operation is 1. The cost of any deque operation is 2, for removal from main and possible removal from min. The cost of an enqueue operation is 2 plus s, where s is the number of elements removed from min to find the potential function phi equals min. Now consider a sequence O1, O2, OM of operations and let Ci denote the actual cost of operation. OI. Let phi I denote the value of the potential function after exactly I operations. Let phi 0 denote the initial value of phi, which here is 0. Define the amortized cost CIF operation instance OI to be Ci plus phi I minus 1. We claim that Ci less than or equal to 2 for every I. If we show this, then we know that the actual cost of the entire sequence of operations satisfies. MIM. Computer Network Assignment Help.com. This yields the needed O, M amortized bound. To show that Ci less than or equal to 2 for every I, we consider the three types of operations. If OI is a find min operation, then Ci equals 1 plus phi I minus 1 equals 1 less than 2. If OI is a deque, then since the lengths of the lists cannot increase, we have Ci equals Ci plus phi I minus 1 less than or equal to 2 plus 0 less than or equal to 2. If OI is an enqueue, then Ci equals Ci plus phi I minus 1 less than or equal to 2 plus s minus s equals 2, where s is the number of elements removed from min. Thus, in every case, Ci less than or equal to 2, as claimed. Alternatively, we could use the accounting method. Use the same actual costs as above. Assign each enqueue an amortized cost of 3, each deque an amortized cost of 2, and each find min an amortized cost of 1. Then we must argue that for any sequence of operations and costs as above. This is so because each enqueue x contributes an amortized cost of 3, which covers its own actual cost of 2 plus the POS Cybele cost of removing x from min later. Computer Network Assignment Help.com. Problem 2. Quicksort analysis.